Okay, so we have a recording as well. And let me see here, 1 second. So. Okay, so now I'm going to share my screen. But maybe before I share the screen, do you want to ask me any particular questions about the homework? We can start with that if you want, so I can make some additional comments. Would that be okay? You prefer that, or you just prefer to do some problems in general?
Problems in general.
What's that? Sorry.
Problems in general.
Problems in general, okay. All right, sounds good. So let me then, I have this. So I have 3 problems that I have created. You see them here. So one problem is something that you will see as a problem is the most difficult, in fact, in conceptually speaking, this problem. I have a spherical surface. I have so the second problem is an electric field that is given by that and wants to find the charge density and units and calculate the total field. And the third problem is a sphere of radius that is centered at an origin and has a particular volume charge. So this is what I have in mind for problems. Do you have any other problems in mind you would like to suggest? Okay, I did not hear anything, but in case you have any questions, just let me know. The other thing, in fact, let me see 1 second here. What's homework? Homework 3. Okay, so this one is very similar to the finite length problem. The only comment that I would like to make is very similar to the finite length charge we have, but now you have 2 of those. So what you're going to do is to apply superposition. You'll do one, you will do the other, you have the formulas, and then you will have to superimpose them. Is that something that is it clear? You will do it like that?
Yes.
Okay.
Yes.
That is the easiest way to do it because you have the formulas. I don't want you to recalculate or evaluate or develop the formulas. You have them. You take them ready. You just you're careful on how you do the superimposition. That's all to it. But it's going to be superposition. And to be careful, also try to do the superposition in the X, Y, and Z system. That's the other guidance I will give you. Don't try to stay on a cylindrical system, but go to an X, Y, and Z system to do the superposition. All right? Okay, so now what I would like to do is to go back to the problem that I had identified, because these problems will help us practice. Let me see. Okay. Problem following session 2. All right, so let's start with this one. Let's see what it says. It says, consider a surface spherical. That is, so I'm going to write here a sphere. All right. And the radius of this sphere is B. And there is a uniform charge on this sphere. So if I just change it a little, make it a little thicker, so you know there is charge on this sphere, Q sub S. and I consider that to be Q naught and to be uniformly distributed. Okay, so what we want to do is to find, so we are in a sphere, all right? So we are in a, I'm sorry, we are in a three-dimensional environment, so we are going to use the spherical coordinate system because this charge is uniformly distributed. Therefore, whatever we find is going to be spherically symmetric. Do you agree with that? So the first important observation is that the field E, wherever it is going to will have spherical symmetry. Okay. Now, and then we need to find the field R larger than B, outside, rather inside, and then we'll have to plot it. So what am I going to do? I'm going to do exactly what I did in class today, where I will define a surface because I will start with Gauss's law. So so we start with Gauss's law. And what does this law say? That the divergence of D equals either with Q sub S if it happens to be at any point on this surface, or with 0 if it's anywhere outside. Okay, so it's like this when R equals B and it's 0 everywhere else, because the charge is only on the surface of the sphere. Okay, so then I will add pages here. So then what am I going to do? I will have to develop to find a volume, because we know from the divergence theorem that the volume integral of this equals the surface, closed surface integral of D dot ds. Okay, and if the volume that I define incorporates my charge, of course, this is going to be equal to the total charge. All right, so but I will write this first. So what I'm doing now, I define a volume. And how do I define the volume? I define it so it incorporates. So I will take, let me take this one in for a moment. I will find it so that it incorporates the sphere. Okay. So this is the volume, V. The surface of the volume is this one, and the direction of the surface of the volume is this. So if this is my surface S, inside here is volume V, then, and I'm in a spherical system, therefore I have defined a volume that is a sphere. It's a concentric sphere with my own, and is a little bit above, all right, it's almost very close. It just covers the sphere inside, so it's very close to my surface. And according to this, in the spherical coordinate system, what kind of vector this is? It associates, it's identical with which unit vector of the spherical system? This direction here. what unit vector has that direction of the spherical coordinate system? Can you tell me?
It should just be a function of R, right?
It's going to be just the A sub r unit vector. Do you see that? That this vector n, which is just a unit vector, is just the direction of the surface, is identical with a unit vector along the radial direction. Is that clear to you? Is that clear to all of you?
Yeah, that makes
Okay. So now I go here, I go to equation one, and I'm rewriting in the volume goes, the volume, first of all, what I realized that the volume encloses the whole charge. So here, from Gauss's law, what I will have before I write here, I will have this is equal to what? To the volume integral of this QS dV. All right. But this QS is on the surface of the sphere. So what is this? What is the total QS? The total Q rather. What is the total Q on this sphere, spherical surface? It's going to be what? It's going to be the area of the surface times Q sub S. Is that right?
Yes.
Okay. How much is the area of the surface? Is 4p b squared. Do you agree with that? That's area
Yes.
of sphere. Therefore, what we have that the closed line surface integral of d dot ds equals 4 pi b squared q sub s, which we called it q naught. It's everywhere. Okay. So now we found that relationship. What we need to do is to find the integral. The integral is a surface integral on the surface of the sphere. And on that surface, d dot ds is nothing else but d dot a sub r ds. Okay? So this one is the radial component of d. And therefore, this, if this is 1 and this is 2, 2 tells me that d is d sub r, a sub r, so it has only one radial component, and is equal, in fact, there is also an integral. Wait a second. We wrote this. So now we have to take 1 from 1, 2, 3, from, excuse me, 2, 3, and 4. What do we find? We find that we have to take the, what do we have to take? We have to take now the integral on this surface S, which surface has a radius r. Okay, and of dr. So we are going to have, since dr is going to be the same, this is spherically symmetric. So everywhere on this surface S that I have the pink one, everywhere on this surface, the value of d sub r will be identical. So I will have the line integral from the above excuse me, the surface integral. So from 2, 3, and 4, I will have that the surface, closed surface integral of dr ds equals 4 pi b squared q sub naught. And then dr, as I said, is independent of phi and theta. It only depends on r. And therefore, everywhere on this surface, the cylindrical surface, which has 1 r, every point on the cylindrical surface S, spherical surface S, has the same distance from the center of the sphere, so it has the same r, but it has different theta and phi. But your d sub r is independent of theta and phi because it has spherical symmetry. So I will rewrite this as d sub r s ds equal to 4 pi b squared q sub naught. Okay, how much is this one? dr is constant, so d sub r, and then it's again the surface, but which surface? The surface of the area of S surface, which has a radius r, not b, r. It's a surface that encloses. We have taken it close to the conductor, but it's a surface that has its own radius. So it's going to be 4 pi r squared equals 4 pi b squared q sub naught. So from here, we find that d sub r is nothing else but b over r squared times q sub naught. And that's what it is. So then D or E, we are looking for the electric field, all right? So E will be 1 over epsilon naught b squared q naught, if you want to see, the r squared. So you can see the r dependence, all right? That's why I wrote it like that. So outside of this surface, put some color so you can see it, the electric field, and as a matter of fact, I have to add also its, well, it's kind of too dark. Leave it like that, I will have to say. Forget that one. Okay, so outside of the surface for r larger than b, the electric field always varies as 1 over r squared. Okay, now we found that. Let's see what happens inside. But before I go inside the surface, the spherical surface, do you have any questions about the kind of derivations we did to get the electric field? Any questions?
When R is less than B, the electric field is 0 because you're not enclosing any charge, correct?
Correct. Absolutely. So that's what we're going to see next. So now, when we'll add one more page. So we went, in this case, we were R larger than B. I write it here to remember it. So now we are going to have R less than B. So here, I'm going to take the same picture here. I don't want to redo it. And then I will say copy. Go here, paste. And what I will do is to change the location of the pink surface. So I will take this and I will change its size to move it inside, okay? And let's see. Oh. No, let me see that. There's this, and it's gonna go like this. This is R, right? I will take this one. Oh, no, not like that. There. Okay, this is B still. And this one here goes here. And this one here goes here. So I do exactly the same, but I have just moved my volume inside. So let's see what happens to these equations. So I'm taking this equation here and see how I will have to modify it. Copy. Because Gauss's law still applies. The only thing is if I am in the new V surface, volume, and S surface, then there is no Q that is enclosed by this surface, which means that this is going to be 0. So what is interesting in all of this? 0. If this is 0, and then I follow exactly what I did here, let me do this. This has not changed. Well, with the exception of Q, but the other one. So practically, take this, copy, paste. So here, since there is no charge that has been incorporated inside the volume, this volume V, this is 0, okay, which means out of this one that this bar equals 0. And what that says is that the electric field inside here, so E is going to be 0 for every R, which is less than B. And if we want to plot it, what are we going to see? So let's plot R here. And that's is a bar. Okay, so, and then let's assume that this is B. So the field that you're going to see, let me find a different color. It's going to be 0 here. And then here is going to jump right around as it goes there. So it's going to start right after B. It's going to start at this point. And that point is going to be this one here. Copy. Okay, so this point here is this one. And in fact, it's going to be just Q sub S over R naught. So let me erase this part. Okay, let me write it here again. It's gonna be Q sub S over epsilon naught. And then from there, it's gonna go down as 1 over R squared. And that's what you get. Any questions for this problem? Questions?
So when like B equals R, like does it like saturate or something? Like
No, it
Um,
starts at the maximum right there when it goes to, it starts at a maximum and then goes down. It's 0 before it,
okay,
but right as you cross the chart, then it starts at this maximum value and goes down to 0 as you move
Okay.
away.
okay, thank you.
Yeah. You're welcome. And what is this here that I have? Ah, there is something here, which I don't know what it is. All right. Okay, so now let's go to problem 2. That's a different, I decided to take 3 different problems, all right? So we just have some variety here. Okay, what it says? We have a field, obviously from what you see here, the field is given by this. Is in cylindrical coordinates. So obviously observation. Number 1, field in cylindrical. Coordinates. Okay, and then says number 1, find charge density and its units. Okay, what do we know from Gauss's law? We know that the divergence of D equals the charge density. All right, I mean, let me see how I'm gonna write charge density. I will write it as Q sub V at this point. This is cylindrical, all right? So it's in 3 dimensions. I will write it as Q sub V. In some other places, you will see it as rho sub V. But because we have rho here, I don't want to put the rho sub V. It's going to get really confusing. So I will keep it Q sub V. So this is the charge density. And the charge density in general, it can be a function of rho, phi, and z. All right? Do you agree? Nobody said that it's uniform. So it can vary. Now let's see how are we going to find it. We'll just take D and we find the divergence of D in cylindrical coordinates. So you take the book, get the book here. Your book has at the end, if you look at the book at the back cover, it has all of the differential operators in every coordinate system. And here, the divergence in a cylindrical coordinate system, it's written like this: divergence of D equal 1 over rho theta rho d sub rho plus 1 over rho theta d sub phi theta phi plus theta d sub z theta z. Okay, which one is d rho D row, D sub row is 2 row Z plus 1 cosine phi. D sub phi equals minus rho Z plus 1 sine phi. And D sub Z equals rho squared cosine phi. That's what we have. So now we're going to try to find this divergence. So let's start with 1 over rho theta theta rho and rho d sub rho. What is that equal? 1 over rho theta theta rho, and then we have 2 rho squared z plus 1 cosine phi. So this is going to be equal 1 over rho 2 z plus 1 cosine phi theta rho squared theta rho, which is 1 over rho 2 z plus 1 cosine phi, and then you have 2 rho. This and this one gives us 2 z plus 1 cosine phi. Okay, let's call that 1. We have called that 1. Then what do we have? 1 over rho, we have to calculate 1 over rho theta d phi theta phi, and this is equal to what? What is d phi? It's up here. So we have 1 over rho theta theta phi minus rho z plus 1 sine phi, which is what? This is minus z plus 1 cosine phi. Okay, this is 2 and 3 over rho squared cosine phi, which is 0. And that's 3. So if we can put 1 plus 2 plus 3 in this equation here, so we have the divergence of D. It will be the sum of 1, 2, and 3. So it's going to be z plus 1 cosine phi. So what is that? That is your charge. So the charge, which is Q sub V. And the charge is a function of R, we set phi and Z, but obviously here is not a function of rho, rather. It's not a function of rho, yeah, but it's only a function of phi and Z. So practically we found that Q sub V equals Z plus 1 cosine phi. Okay. Then what they want us to do is to consider a volume. We are in a cylinder. So we are cylindrical rather coordinates. So this is 2. let me call it then A and B, right? We have too many ones and twos, so this is A and B. A and B here. So we are in a cylindrical coordinate system. The cylindrical coordinate, you know what, I'll make this a little smaller so we don't have to add another page. Okay, that's better. All right, what do we have here? We have a cylindrical system. Cylindrical system is like this. Let me use this one. It's like has. Okay, so take that here. And has an axis Z. All right, so now they tell us to define a volume that where the rho is between 0 and 2 and Z is between 0 and 4. So if this is 4 for Z, then we copy this, copy. No, duplicate. There. And we said that rho is between 0 and 2. So practically we put this 2 here like this and like this. Okay, and that is the volume. So it's like a slice of the cylinder where Z here is 0 and this one is 2. All right, so this one is 4. We want to find out how much is the charge in there. So to do that, we will have to integrate in the volume. So we will have to find the volume. Oops. And the volume in, what did I give you? Let me go for a second to see how much is the volume in cylindrical coordinates. You're gonna go into our one of the classes that I gave the so if you got one of your sections, so in one of the early second week, I talked about vector properties. No, it was not that I'm gonna ask for. It was not that. In here. I have now put sorry, it's I am looking at the wrong material for a moment. So it is in the second week. Look at these two that I have here. The coordinate system transformations and useful relations in various coordinate systems. All right, so the coordinate system transformations is something that I put recently, and I will look at that so to show you what I have. This is this one that shows how you're going to go from one coordinate system to another. So Cartesian to spherical to cylindrical, the first one. Cylindrical to Cartesian, Cartesian to spherical, spherical to Cartesian, all of this. It's all here. That is one of these documents that this one I put it like recently. The other one that I had put from very early when we started the class is the next one below that says useful relations in various coordinate systems. Okay. Here we have a differential length and differential surface. So in a cylinder, to be able to find the volume, we will have to integrate along the surface and then along Z. So we have to integrate along rho and along phi, and then we will have to integrate along Z. All right. So you remember this relationship here. These relationships, we can find them also from the cylindrical system, but I mean, if you cannot derive them, I would say you come here and then you find what is the expression of a surface in a cylindrical system. But now let me show you, for example, how I would do this without having to go that. In case you don't remember, you can come here, but if you don't mind deriving it yourself, how a volume looks in cylindrical system, you can do it easily there. So let's try to do it without copying anything. Okay. So to be able to derive, to find the volume, first of all, the easiest thing is, it would have been, all right, I mean, if it were a uniform, you will see here that that it does not change with respect to R, but it changes with respect to phi. So for every R, you have the same value, but for phi changes. So how are we going to find a small, how are we going to define a small volume here? So practically, you define it as follows. And then it goes like this. Okay, this is a volume. However, because there is no variation with respect to R, see how I'm going to define a small volume here. What I will do is, I will do the following. I'll move a little bit here on the other side, so I can show you. Okay, so if I draw a line which goes along the rho direction for the same phi now, all right? So phi has not changed. If I were to put the coordinate system, the Cartesian, so I can define. So this is going to be my x. This is going to be my y, and the other is the z. And this would be phi, all right? You remember? And z here. And R, rho. For every rho, the value is constant. For every rho, for the same phi or phi. So I can draw this line, and then what I can say is the following. Then I can consider a differential phi like this. All right, it's like a slice like that. And then I will draw it from underneath it so you can see it, how it looks, but in reality it has to be inside the volume. Maybe, let me see, I don't do it well there. 1 second. Let me show you. Now after I show you phi, I'm gonna erase it so we'll make it a little easier. Then I will take, so this is d phi. This is rho though. And then I take a differential z. Okay, so this is dz. So practically, it looks like a piece of cheese here. It looks like this. Why did I do it like that? Because I don't have to integrate along the row because there is no row variation. In fact, let me just draw it a little bit like this. Variation, this is d phi, this is dz, and this is rho. So that's how it looks. This thing there that I have put inside it looks like this here. Now, if I have that, I can find how much in this differential piece of the piece of cylinder here is the charge in here. So for example, the charge in here, so I will call that dq, it will be let's assume that it starts, it's going to be z plus dz, okay, the value, and plus 1. And then it's going to be a cosine phi plus d phi. Oops. In fact, the way I will do it is, wait a second. No, that's not exactly. I will do it even one step easier. I will assume that this is so small in terms of d phi and dz. So practically dq there is going to be z plus 1. I will assume that this is not going to change. Z plus 1 is going to be cosine phi because I have made d phi and dz are very small. But then it's going to be the area practically of this one. And then I will find how much is this area, and then practically multiplied by dz. But this is like a triangle. And this triangle, the area there is going to be, so practically, because this is very, it's going to be almost a row, which is this, and d phi divided by 2. All right. So why did I say, let's assume that you had this triangle here. Let's assume that you had this triangle here. All right. And that was the height, and that is the base, d phi. Now, because it's so narrow, the height and the two sides are about the same. So the area of this triangle is 1/2 the base times the height, which I put, it's rho, practically, very close to rho. So the volume, the charge in this infinitesimally small volume, so from here, the total charge in this dq is going to be z plus 1 cosine phi times the volume of this small slice, which is going to be rho d phi divided by 2 times dz. So it's going to be rho divided by 2 d phi dz. So that's what it is, this slice. Okay, now that I found how much is this slice, to find the total volume, I will have to integrate from 0 to 2 pi phi and from 0 to 4 dz of dq practically, which is z plus 1. I will have to integrate that dq practically. Z plus 1 cosine phi rho over 2. Okay, so that's what I have to do. Find the total, excuse me, not the volume, the total charge in the volume. The total charge in the volume. Q total. Okay, so how do we do that? So it's going to be rho over 2. All right, and rho is going to be 2. It's the whole dimension that they gave us, but say rho over 2. And then it's going to be from 0 to 2 pi cosine phi d phi and from 0 to 4 dz z plus 1. So that one is going to be, you remember how cosine goes? Cosine goes like this. So practically, when we take the integral, let's suppose 0 to 2 pi. Did I miss something here? Because otherwise, if you integrate, that gives you 0, which is not true. So I think I have missed something in those calculations that I've done. And maybe,
Dr. Katehi,
yes,
I think the volume differential in cylindrical coordinates is rho d phi dz instead of rho over 2. But there's also d rho as well.
okay, so rho d phi dz.
Z. Yeah, I think that's the volume differential in cylindrical.
Okay, so, okay, well, thank you. So obviously I missed something here. So in that case, I will leave it like that. I will go back. And what I will do is, but in this particular differential is not like this. Then in this case, we're going to change the differential. We're going to make the differential on a cylinder. Is not like this that I try to do it, but it looks like that. Okay, that's the differential of a cylinder when you integrate along all three. I try to avoid integrating along rho, but so obviously I had a problem somewhere. So this is now the differential if we use that formula. So this one. And to do this, to find the volume, we will have to integrate from 0 to 2, from 0 to 2 pi, and from 0 to z. And then we are going to have rho d phi dz, and q, which is z plus 1 cosine phi times rather. All right. I think d phi is the same thing. So what is interesting here, you know what is happening. That's why even in the previous case, it was correct that it was 0, because we'll do it carefully now. But look at this. So we have, and then we'll explain why. So practically, we integrate the total charge in this piece of cylinder, slice of cylinder. So it goes rho d rho, 0 to 2. It goes 0 to 2 pi cosine phi d phi. And then from 0 to z, z plus 1 dz. How much is this one?
Oh, that is 0, yeah.
Yeah, see, it comes out to be the same. And why it is 0? It's correct that it's 0 because the charge changes its polarity as you go around phi. So from 0 to pi is going to be positive. Excuse me, from 0 to pi over 2. And then from 3 pi over 2, so this is the, assuming this is the base. This is where it's 0, pi, and this is 2 pi. Cosine is positive here and there. So on the lower part, it's going to be positive, but on the other part, it's going to be negative. So if this is positive, there is going to be negative. So yes, it's different in every area, but when you integrate the whole thing is 0. See? That's why it comes 0. It comes to be 0, and it's correct. It's correct, the correct result. Okay, so the total charge is 0, which we should have seen, I have to tell you. That's why sometimes what happens when you look at math and you don't, which happened here, if you decouple from the math for a moment, we should have seen this way before, ahead of time. In fact, we should have seen this here from here. If I did not go directly into math, I would have said, this one, the way the charge varies, is going to be practically 0, the integral, the total charge inside this cylinder, slice of cylinder would be 0. I would have seen it immediately because the integral of a cosine phi from 0 to 2 pi is 0. But it doesn't matter, we proved it also. So that is it's an example of how you it's a little bit of practice of how you do differentiations and integrations in a cylindrical coordinate system while you apply the Gauss's law. You know what else we could have done? Oh, he asked us, first of all, they asked us to find the charge separately. That's why we did that. Okay, we had to do it anyway, the way they asked to solve the problem. Any other questions about that?
I had a question about part A of solving this. For the first
Yes.
equation that we found, isn't it supposed to be 4z plus 1 cosine instead of it being 2? I was a little behind with copying it down.
It's
I got to
negative
that.
here. So if I'm right, there is a negative sign here. So negative.
Well, it's a little lower down.
No, I know, but here, d phi is negative. And there is a negative sign here. And where did you find the 4?
It's solving the first equation where you have 1 in parentheses. The one right above it, it says it's 2z plus 1 cosine phi and then 2 rho.
Is this wrong here? Oops. 2 rho. Is this correct? Yes, go ahead.
Isn't there like a factor of 2 missing from like the derivative, the partial derivative? I think I see what she was saying.
Here is
I
I think that's
D5.
on the
This,
page below this one. Or, yeah, where you're solving right here, where you're finding row D row, and then we have 2z plus 1 cosine phi. Right above it, it says that there's two 2's that I thought were supposed to like be multiplying unless one of them gets canceled out.
there, 2 wrong. Let me see. Let me ask you before we go. So this, do you think this is this correct?
Yeah, I would say that part is
That's correct.
correct.
Okay. Yeah, yeah, good. Okay. So then we have, yes, we have 4. Ha. Now I saw it. Thank you. This one here. Yes. Thank you
Yep.
for correcting me. Yes, 4 here, 4 here, 4. Okay. So then, so we have 4 from that. Mine, so it's 3 practically. There should be a 3 there, isn't it?
Yeah.
Yeah, thank you. Okay, and then the rest is 0. Okay, thank you. Yes, you are correct. All right, any other questions on this?
Professor, could I ask a question about the top hat exercise we took this morning in class?
Yes,
So the solution for this exercise appears to have been posted,
yes,
and it says that the correct answer is A, and I was under the
yes.
impression that it would be F.
Do you want me to solve it?
If you could, please.
Of course, yeah. Let me then go up here. Wait a second. I'll add the page here, add the page, but then I will move the page. What happens? I will take all of this. Okay, so this is the exercise. And it's number 5, isn't it?
Yes, it is.
Yeah. So what it said there is the following. We have a wire. A wire that looks like this. So instead of being straight like this, we have curled it. So this is one, and I'm gonna do also the straight wire because it's gonna help. So this one is like that. Okay, and then it asks us to go and say what kind of field we're gonna have here. And here we have, remind me, which direction? This was X.
Y is going to the right.
Yes, Y, and then Z was coming out.
Yes, ma'am.
All right, perfect. Okay, now let's try to take to see exactly what is happening. Let's try to take a straight wire. All right, so I'll take this one and change it like this because that's what we found. We solved. Let me, in fact, erase that for a moment, and then I will turn it around. So this is the problem we solved in class. So style this. Okay. What did this is A and B. So I'll say A and B. All right. What did we find when we solved that? We found that the field around this goes in a radial way. All right. So practically, if I am here, if I am on this plane, let's assume that I have now defined if this is Z, and in fact, I will not have it Z. I will have, let's assume I will have this one as being Z for a moment. No. Wait, I'm trying to use, I will use this one as X. I will use this one as Y. Okay, I'm getting there. Y. And then Z is gonna come out. So this one is along the Y direction. All right, and if I have that, let me also erase this for a moment. If I have X like this, Y like that, Z is gonna come out of the so Z somewhere is gonna be like this. All right, practically it's gonna be here. Now, what did we find when we solved that? We found that if I am on somewhere here, let's assume that I am somewhere here. Here. Then we found that the field, if this is like positive Q practically, that the field here is going to be along that direction, all right? And when we took a piece of, when we were deriving this and we took a piece of this wire here, we found that here the field at that point would be like that. And then when we took another piece of the wire here, we found that it would have been like this. Okay? Do you agree with these observations on the straight wire?
Yeah, I agree that that all makes sense. My confusion was that in the assignment or in the exercise, it wants us to evaluate a point that is elevated on the z-axis. So
No, but it does not say where the wire is still at the same. It says that the whole thing, where am I reading it? If I, let me go back and read it for a moment, if I may. So, okay, what does it say? A uniform line charge of density has the form of a semicircle of radius A lying in the XY plane in free space, as shown in the figure. The electric field intensity vector due to this charge at a point on the z-axis defined by the coordinate can be represented as, it does not say, so the way it shows it, it's the same, it all is on the same XY plane. It's
I
just
was
that
just confused by the aspect that said the point is on the z-axis and it's defined by the coordinate z is equal to a. So
Yes.
I was under the impression that the point is with the way the coordinate system is drawn, I was under the impression that the point is out of the page, elevated above the XY plane. And so I thought that the semicircle ring of in the XY plane would the electric field intensity due to that at a point that is at A on the z-axis, the points or the electric field intensity vector would point also in the z direction, therefore giving it a z component.
Same here.
Okay. Yeah.
I
It's
also thought it is F for that reason.
what is it?
Uh,
Oh, you found that. No, the problem is the fact that Z is A, it does not say that your line charge is at Z equals 0. Okay, it's on the XY plane. Now, why it gives Z equals A, it's, I don't know why. I mean, you know, it's from a book that I that has a number of conceptual questions, but because let's assume in this particular case, all of your field will be here, all right? Will be like this one. Now, let's assume that you are correct, that it was elevated up, but that would assume that your line charge is at the at the z equals 0 plane.
Professor, if I may, I thought that's what it was meant whenever it says lying in the XY plane. I thought that inherently meant that the line charge is at z is equal to 0. But that may
That's
just
not
have just been
so.
a confusion on my part.
Okay. Okay. It's not very clear, obviously. And so you assume that you will have, what did you assume you will have then? Which one
As
of the
my
two?
answer,
Mhm.
I said F, so that there would be a positive electric field component in the Z direction, and then there would also be a component in the X direction. I'm aware that
But
the components in the Y direction would cancel from both sides of the semicircle.
But why do you think it's going to be a negative component in the X direction?
Because it said that the Q prime, the elemental charge element, would be positive, so I would think that the field lines would emanate
Because the
outwards.
direction, yes, of
Yes,
course.
ma'am.
Yeah. Okay. Well, if you think it that way, of course, it makes sense. It would make, what I can go and do in the problem in retrospect, I can, what section you're in?
501.
501. I can go in this edit. I mean, I took it for granted it was on the same plane. Okay, so unassign, if I were to unassign that. Yeah, see, I took it for granted it was always there, but I can edit it. And I can make this also the correct answer. And what does that do? If I do that, say, and then, okay, what is it? Correct answer and save. So could you check your grade to see what you get?
Yes, thank you, Professor. I'll check it.
Yes.
It appears to have updated and it says I'm correct now.
Excellent. Good. Oh, well, thank God
here.
for this. I need, I need to make sure to remember that I clarify that either I remove, I just took it term by term. I took it for granted, to tell you the truth, that it was on, all of them were on the same plane.
I got you. Okay. Well, thank you for
Okay.
clarifying.
Sure. So at least, what I did is that in this one, if you have either of the two solutions will be correct. So because if it does not say that one, I mean, unfortunately, it would have been a lot better if it had said, or if I had corrected to say that one is at z equals 0 and the other is at z equals a, or they're both on the same. But in any case, I fixed that. So probably I
Cannot
would
see
have.
the exercise anymore in top hat.
Was that?
What was the number for this exercise? I cannot see it anymore in top hat.
Yeah,
You-
mine is
you-
missing too.
Because I unassigned it. Otherwise, I have to assign it again to be able for you to see it. Just a second. So assign as a review, all right? So you can see it. And in fact, since I did that, let me see the other class. I will have, in case, is there anybody from 502?
I'm in 502.
Yeah, me too. I'm in
Okay.
502.
All right, let me go then there for a second.
And also, I don't think I get the grade from the exercise 5.
What is it?
I mean, I don't see anything related to exercise 5 in the grade book. I mean, I don't get the grade from
And
the
what
exercise 5.
section are you in?
502.
Okay, wait, let me get there for a second then.
Yeah, thank you so much.
Yes, just a second. Okay. Okay. No, sorry. In fact, since I get let me just edit it. I just want to put the name, the number is 5 in for a moment. 5. Okay. Okay, and now I have to save it. Where is saving? There. Okay, can you check it now? And then me assign it. Can you check your grade? The ones, I don't know what you responded, the other two who were at 502, but I will assign it as a review and see whether you can see it.
Yeah, I can see my grade now.
Okay, should be taken care of. See, that's what happened. Half of the people, that's why half of the people who did A and the other half did F. Because, yeah, interesting. You know, the interesting thing is in my other class, when I gave that, everybody took it that they were on the same plane. Is it not interesting? Last year, because I gave that last year. That's okay, but it's good. I will make sure that I will keep it that way. Okay.
Professor, hi.
Yes.
In regards to the team arrangements, until yesterday, I was with the same team that I was assigned initially, and I checked it
Yes.
again yesterday.
And today what happened?
I was moved to another group after we already finished the assignment together.
Okay.
So we already got together earlier, and we worked in an assignment.
So why is that? Because somebody, let me go back. You are 501, are you?
Yeah. I sent you an email also with the names.
Oh, you did? I have not seen. When did you send me the email?
About an hour ago or hour and a half.
Yeah, no. I will see it much later today, but they might go to people, and is it 501? Let me see. Yes, 501. And go and this. I have to tell you, they asked me in 501 to make so many changes. And then I don't.
Until yesterday, I thought
it was okay. Okay. Tell me. So which group were you before?
I was in 9 and now I'm in 8.
Okay. And now you're in 8. I moved you because there were 2 and 4.
We already worked in the assignment. We put the
Okay,
efforts to
let
get
me do
together.
something else. All right. So you want to go to 9?
Yeah, we already did the assignment, but when we get to submit it, I didn't find my name there.
No, I understand. But so you want to go to 9. That's what I'm
Yes,
saying.
with the same
Okay.
people.
Yes. Yeah. What says? Yes. Let me see 9. What happened? Okay, then I need to find somebody. What am I going to do with these 2 students?
Hi. So for about like the past week, I've been trying to request to be put into group 8.
Where,
I-
where are you now?
I'm in group 6.
And you are in 501?
Yes.
Okay. And your name?
Santiago Cantu.
Ah, yes, Canto. Where do you want to go?
Group 8.
Ah, okay.
Yeah.
Make my day.
So it is
Yeah,
called.
it's perfect.
That's
Thank you.
perfect. Okay.
Thank you.
Oh, good. All right. Yeah, that is quite something, trying to make changes around.
So
you know, trying to-
they
okay.
they already submitted, one of the group of 9 submitted the assignment, the group assignment. So that means
No,
that
that's okay. So now you're gonna be part of that group when I do the grading.
okay, and also the name is in the assignment. We put all our 4 names there.
And in the where was that, in the 6?
What
You
do you
were,
mean?
I mean, when you submitted the assignment, what group were you in?
I was in 8, but I sent it to one of the group in 9 to submit it, so that the assignment to be submitted in group 9.
So who is talking now? I'm sorry, Assam, it's you. I'm sorry, I could not differentiate your voices for a second. So Assam, you're talking to me, isn't it?
Yes, I'm talking to
Yes, okay. So what you're saying is that when you were in group 8, but
Hello? I cannot hear you anymore, Professor. I think you're muted, Professor.
Professor, are you there?
Oh, I don't think she's hearing us.
you cannot hear me because I was bumped out of the other. So let me connect and you're gonna hear me again, okay?
We can hear you right now.
Yeah.
Yeah, now, but I have to connect to the other one. Just a second. Can you hear me now?
Yes.
Yeah, perfect. Okay, sorry about that. I was bumped out for some reason.
So now I'm in the correct group 9.
Yes, what I was asking you is the grade you're gonna receive now is from group 9.
Okay.
Is that's okay?
Yeah, because the one
Ah.
who submitted is one of the people in group 9.
Okay, perfect. So we're good in
All
that
right.
case. Yeah,
Thank you.
you're welcome. Okay. So we were looking at the teams right now. And which team were we at? The 502. Could you remind me the last thing that we were doing before I bumped out? I
Oh.
was bumped out of
Oh,
the.
we were just talking about the teams.
Okay. And so is there anybody else who needs a change with the teams? From those of you who are here? Okay, so nobody's there. So now that we resolved that problem, so do you want to go to problem 2? Can you hear me?
Yes.
Okay, perfect. I mean, I'm asking because you never know with this. So got here. All right, so we did. Let's do the last problem, all right? Okay, it says a sphere of radius alpha. So here, it's more of the same. Alpha.
Professor, we
You're not sharing your screen.
Oh, thank you. Okay, so we have this sphere and it says the radius is, okay, so it has a radius alpha and the charge distribution is 5 square root of r, of r, right, and 0 outside. So practically it's here, the charge. And we want to find the field everywhere. It's not any different from what we did before with the first problem, but all right. So we start again with Gauss's law. Rho v, wherever it exists, and 0 anywhere else. So practically in sphere, in. So when I would say the way to show that is when pressure equal to alpha and r larger than alpha. Okay, so we will do the same thing. Since there is only a variation with r, that means that this one is going to have a spherical symmetry, meaning no theta, no phi in the solution. So the field is going to also be a, so this is what is going to be interesting, all right? So the field is going to be a function of r inside, but it's going to be constant out. I mean, it's going to be a function of r both inside and outside, but it's going to be a more complex expression for r inside because of the way the density changes. We'll see how we're going to do that. So first of all, let's try to find what is easy. We are going to consider a surface that is just outside of this. This is more like the first problem, but with a little more complex density. So that is going to be the outside surface here. And it's going to have that kind of direction N. And this is surface S. And then it encloses this volume P. So practically from the divergence theorem, all right. Now, let's take one at a time. This one here is going to be equal to the surface, closed surface integral of d dot ds. And this is gonna be the volume integral of, and remind me how much is the volume. It's gonna be the volume integral in spherical coordinates. You have it there. Is going to be practically, do you have it in front of you? Let me find it from the book. Okay, let's see, is, all right, is r square, one second. Is, I believe, r squared sine theta d phi d theta dr. Is that right? Let me just confirm it. One moment. From the book. Let me see. I'll make sure that we are not wrong in this one. Is r let me see, here it is r squared sine theta. Okay, all right, so, and the volume here is gonna be r squared sine theta dr d theta d phi. So it's dr d theta d phi. Okay. And so this is going to be equal to 5 square root of r squared dr, and then sine theta d theta from 0 to pi, and then 0 to 2 pi d phi, and 0 to alpha. Okay, just check me out to make sure that I don't make a mistake somewhere. Do you agree with that? So then, so we're trying to find the charts here, how much this is. So we have 5, 0 to alpha r. So it's 5, it's 1 over 2 plus 5, this. And then we have dr, and then 0 pi sine theta d theta and 2 pi. So here we have, that's Q. So then we have phi, and then 0 to A, and then we have R. So 7 to D, and then we have 1 over 7 over 2. All right. And then we have 0 to pi, and then we have minus 1 d cosine theta. Just check me out to make sure that I'm doing correctly. So it's 10 divided by 7, r 7 over 2 from alpha to 0. Can you hear me? Can you hear me?
Yes.
Okay, perfect. I'm sorry, it was very quiet and I thought that you could not hear me. And then is minus 1, and then is minus 1, that makes minus 2, and with this one, this is 2. So practically it's 20 over 7 alpha 7 over 2, which makes like 20 over 7 square root of alpha. That's what I think is coming up from Q. And then we have the surface integral of ds, d, and we said that d is going to be independent of theta and phi. So practically is because of the charge is independent of theta and phi. So practically is going to be the area, which is 4 of the sphere. 4. So from, if we call this one from 1, we have 4 pi alpha, no, r squared, dr is going to be 20 over 7 square root of a cube, which in fact gives us the d as a bar is going to be 20, 28. Is there another pi? I forgot the other, this pi.
Yeah, I think it's, isn't it 2 pi?
2 pi. 2 times 5 is 10. Ah, yes, 4. Another one. Yes. Thank you. 20 here. 20 pi. And so 40 here. 40. Okay, so practically I needed another 2 pi here. Times 2 pi. All right, so this and this gives a 2. And then I change that to 10 over 7. And then what do I have? I have am I correct here? That's what I got. So assuming that this is correct, the calculations that I've done, what you find is that your D has only the D sub R component and is given by this. So practically outside of the sphere, it changes as 1 over R squared. Okay, so that's how it goes outside of the sphere. And then the rest is a constant, 10, 7 squared of A cubed. Now, inside the sphere, it's a different story. It's like the first one we solved. So you take this one, and then you copy it, and go here. And then what we do, we move that inside. We move it to a distance. We select any distance, and we call this R. Okay, now, everything that we've done before is going to be the same with one exception. That first of all, let me take this one. Copy, take this one down. So practically we have inside that volume V. So this is V and this is S. And this one here goes here. There. Okay, so we have that inside volume V. And so when we apply the divergence theorem, it's going to be exactly the same we found for Q, but instead of alpha, it's going to have R. So it's going to be exactly this one here, but I forgot the 2 pi. Did I put the 2 pi here? 2 and 2, 10, 20. Now that's correct. Okay, so it's going to be like this, but with R. So there. That. But this, instead of A, we're going to have R. R. So we, this one, because it's going to be also the same thing, it's not going to be a function of theta and phi. This one here is going to be 4 pi R squared, d sub R, and it's going to be 40 over 7 R to the cube square root of R. So practically this one and this one is going to go. This one and this one makes 10. Do we have another pi from Q? Yeah, there is a pi here. Pi. Okay. So there is a pi here. So d sub R is going to be 10 over 7 R square root of R. So inside the volume is going to change like this. which means that if we were to plot this, it's going to start at 0 up to alpha, and is going to grow faster than linear. Like this. So, and then from there, it's gonna go down as R square. It's gonna look like this. So that's how it's gonna look. Any questions about this? Practically, it's Gauss's theorem, you know, just implementations of Gauss's theorem. Just trying to be careful with the math and with the coordinate system, trying to get the correct surface or volume in the Cartesian and cylindrical system, excuse me, spherical and cylindrical systems. Any questions about this? Any other questions, just general? Any other questions? Any questions? I will check this out to make sure that I will go through the derivations once more, and then I will try sometime before Friday to put them up on the web, and I think I will, if I don't find any mistakes, I will put also the video, because if I find any additional mistakes here, then the video is not gonna be good if I use it. Any questions? Is this helpful?
Yes.
Yes.
Okay,
Yes.
good. As long as it's helpful, that's the only thing that because I think it's best, you know what I was thinking? It's best if I do it in real time, because if I have it prepared, we go through fast. In real time, you also follow me, and the fact that you can correct me is also very useful, because you can follow what I'm doing, and then it's a lot easier to learn this way, as opposed to me having it and having corrected all of this ahead of time and come and just go through the derivations. It's better if we do it in real time, don't you think? So the question is, do you prefer me that I have solved those ahead of time, or do you prefer me that I do it in real time here?
Real time.
Yeah, that's what I was thinking. Because it takes it slows me down anyways. The one thing that I found on the book, there is these formulas are on the summary. If you look at the summary, which is on page 97, it has the lengths, the areas, and the volumes in the 3 coordinate systems. And I think what I will do, I will probably try to make a copy of this and then upload it, so it's easy to find them. Okay, I think that's where we are. It's almost 6:30. Let me know if you have any other questions or anything else. How else can I help?
I have a question.
Yes, go ahead.
For problem number 1, I was just kind of confused on where we got the b squared on top of the electric field.
B squared. Okay. The B squared came out of the charge. From here. The charge is on the surface of the sphere. And because it's uniformly distributed, it's just the surface times the charge density.
Okay.
Okay, yeah. Any other questions?
Thank you, Professor.
All right, you're welcome. So I will see you on Friday.
Thank you.
Okay, bye-bye.